Welcome to a new time series analysis and forecasting tutorial. Today I'm going to show you how you can compute impulse response functions using the local projection method. We're going to be using STATA as it is a software that everyone seems to prefer.
If you're passionate about understanding data and the economy, you are in the right place. Before we start with today's tutorial, I would like to invite you to hit that subscribe button. It's free and it really helps the channel grow and reach more people like you.
Let's begin with an overview of the tutorial. I have decided to split the content into 4 videos, so please make sure to watch the 4 tutorials to be able to understand local projection methods. In video number 1, I'm going to be going through an introduction to the local projection method. In video number 2, we're going to be doing the estimation of a vector autoregressive model, and we're going to compute the impulse response functions. In video number 3, I'm going to show you how you can extract the structural shock from the vector autoregressive model. Finally, in video number 4, I'm going to be going through the estimation of the impulse response functions using the local projection method. We're going to be comparing the two outputs, that is, the impulse response functions that were generated using the vector autoregressive model and the local projection method. And finally, I'm going to be talking about some extensions, some of the things that are being done in the literature, which is using nonlinearities, is using state dependence, and also identification of different shocks. So those are going to be the 4 videos. Let's talk about the local projections. It was introduced by Jorda in 2005 to estimate impulse response functions as an alternative to vector autoregressive models. The key idea is that we are going to estimate the impulse response functions directly via a separate regression at each horizon of future outcomes on the shock. So instead of having a system of equations as we do in the vector autoregressive model, here we're going to be computing linear regressions in a separate way. There's a couple of advantages over vector autoregressions. Those are that it requires fewer dynamic restrictions than vector autoregressive, so it's more robust to misspecification of the model. It's very easy to change the dependent variable and the control variables as we are estimating individual regressions. Remember that when we compute a vector autoregressive model, we have a system of equations where each equation contains the lagged values of the other endogenous variables in the model. Whereas using a linear regression like we are going to be doing with local projection, we will have the possibility to modify the dependent and independent variables in our model. We can also use shocks that are identified outside a vector autoregressive model. As an example, I give you a very classic and very relevant for the literature, that is Romer and Romer in 2004, where they use a narrative approach to identify monetary shocks. And finally, something that is very cool about local projection methods and is very used in the literature, and if you're thinking in writing a paper, an economic paper, a paper for your graduation, your master's, or whatnot, be aware that it's a topic that is very fresh. It's been used a lot and is basically introducing nonlinearities in your model and allowing for state dependency using a dummy variable. So the idea of a state dependency is that we are going to be including a dummy variable for periods where there is, for example, high activity versus low activity, high employment versus low employment. And the idea is to be able to test whether the responses of the variables to a shock are going to change depending on what's the current state of the economy. Think about, for example, a monetary shock. Is it going to have the same effect in the economy if there's a period of low employment versus a period of high employment? Is the central bank going to be able to control inflation the same if the economy is going through a recession over an expansion? So all these are questions that we can test using state dependency incorporating a dummy variable. Let's look at the math of the local projection method. For each horizon, we're going to be estimating by OLS the following regression. We have first our outcome variable at horizon h. We have a constant. We have here the shock, where this is the coefficient of interest, which is beta, and it's going to be the impulse response at horizon h. Then we have a delta that is going to be including lags of our dependent variable. We're going to be having phi, that is going to be the coefficient of our control variables. All the control variables in our regression are going to be expressed under this x vector. And this is the number of lags that we are including in each of the variables, that is in the dependent variable and in each of the control variables. And finally, we have an error term. So the impulse response function is the sequence from beta 0 to beta h obtained from h plus 1 separate regressions, one per horizon. There's something I would like to discuss briefly in local projections, that is inference. There's a problem with local projections, that is that the residuals are serially correlated by construction. Overlapping forecast horizons induce a moving average structure of order h-1 in the errors, so standard OLS inference is invalid. So there's a standard solution used by Jorda in the local projection method, that is to compute standard errors using a heteroscedasticity and autocorrelation consistent estimators. This is going to correct for heteroscedasticity and autocorrelation up to a chosen lag truncation that is typically at least h-1. This is going to correct for serial correlation in the residuals. It's going to give valid confidence intervals for impulse response function. So sometimes what happens without this is that the statistics and the confidence bands are usually too optimistic. They are going to be biased. There's going to be a trade-off between local projections and vector autoregressive models. That is that the confidence bands from local projections are typically wider than those from a vector autoregressive at longer horizons. I am mentioning this because when you are working with local projections, you're going to notice right away that at longer horizons, the confidence bands are going to start looking wider. This reflects greater robustness to misspecification, as the local projection does not impose dynamic restrictions of a bar. There's an alternative to using the HAC estimators, that is using bootstrap methods, for example, block bootstrap, which is widely used in practice and can improve finite sample inference. So the HAC estimator that we're going to be using for local projection is going to be the Newey West. I'm going to be talking a little bit about this once we get into STATA, but it's something that I wanted to discuss briefly because, as I mentioned, when you're working with local projections, you're going to notice that the confidence bands can look wider at longer horizons. There's the Newey West is the standard used in the local projection, but you can also explore bootstrap methods. Many authors have used bootstrap methods, so I thought it was worth mentioning this in the video. Something important for this tutorial is that I'm going to be using the local projection extension by Ugarte-Ruiz. It's worth to mention this because STATA 18 and STATA 19, they include a built-in local projection command, that is the LPIRF and the IBLPIRF. However, this assumes that the shock is part of a system of equations and they do not support panel data. I believe that the extension from Ugarte-Ruiz is very rich. I would recommend you using this extension because it overcomes many limitations. For example, it's going to allow for exogenous or pre-identified shocks. It's going to support instrumental variables, supports panel data methods, and also something very cool is that it allows different types of graphs, multiple IRFs in a panel, for example. So it's definitely a package that I suggest exploring and I'm going to be using. So in STATA, very important, this is the command. I want you to go ahead in STATA and I would like you to install the local projection package because we are going to be using this in our tutorial. To conclude this tutorial, I'm going to give you hints of what we are going to be doing. We're going to be replicating figure 1 of Jorda 2005. So the tutorial is going to follow these steps. We're going to estimate the vector autoregressive model of Evans and Marshall 1998. This is what Jorda does. He replicates this vector autoregressive model, one of Evans and Marshall. Then we're going to extract the structural shock via Koleski decomposition. I'm going to be using the local projection package. We're going to be comparing the local projection impulse response functions with those generated by a vector autoregressive. And then I'm going to be talking about the extensions and final remarks. Like I mentioned, the extensions are state dependency and nonlinearities. This is going to be all for tutorial number 1. Please make sure to watch tutorials number 2, 3, and 4. If you like this content, please remember to subscribe, and you can find all the material for this video in the description of the video. There's a link where you can buy all the files, the tutorial, and all the information of local projection. I'll see you in video number 2.